Hello and welcome. I'm excited about today's video because I feel like I've been building up to it for literally months to finally share my esports Lambda collection. Um, the reason it's taken so long is because I was really hoping to be a little further along in my, Lambda introduction videos so that I could feel like you would really, someone starting from nothing but watching those videos would be ready to understand everything that was going on here. And I think I've basically failed at that. But I'm also conscious that uh, well, A, that I've shared some of these in smaller groups, and I don't want to, put the outsiders, so to speak, at a disadvantage. And B, I'm conscious that we're only just over a week away from the qualifier round for the MEWC, and so it only seems fair that I share these now so that people who want to use them for that have a chance to do some practice. So, uh, I publicly stated yesterday that I would definitely get this out at 9 a.m. Eastern today. It's now 9:30, and I've just started recording the videos, so it's going to be a little bit late, but I guess the commitment still did its job because otherwise I would probably just have said, "Oh, I'll put it up on Monday." Anyway, so uh, this is, aside from this random introductory page, this is the file that I'm going to be posting online. It's got some kind of examples. So all the lambdas, they're not even all lambdas as you'll see, but all the stuff is here. And then there's sheets for individual pieces explaining what's going on. You can see from the fact that there are still grid lines here, which is like one of the first things that I think to turn off, that the actual presentation of this has been pretty rushed, but whatever. It is what it is. I guess the one other thing to mention on the history of this is, for the most part, this collection was written in one go on the plane on the way to Las Vegas last year, or actually on the way to Tucson, because I went to Tucson first for the MECC. Um, so I had done some thinking before that of like what things I wanted lambdas for, but I haven't really added to it over the kind of year or so since. I probably will add a bit more to it before this year's competition, but that might again not happen until I'm on the plane on the way there. So like there are some obvious gaps, there are some obvious kind of shortcomings of the functions that I'll possibly touch on as we get there. Like the one kind of standout one is there keep being cases about arrows, and like if you start in B3 and you shift up into the right, where do you end up, and that kind of thing. And I don't have anything for that, or not directly anyway. So anyway, yeah, enough chit chat. Let's dive on in. So the first kind of pretty simple ones are just some lambdas for dice. There's one which is not a lambda at all. It's just an array constant, uh, which just gives you, oops, I need the other equal, which just gives you the list of the 6 dice. Just a kind of good reminder that you don't actually need you don't need lambdas for a lot of stuff. Sometimes just having a useful defined name can be quite helpful. So in other words, if I didn't have this pips function, I could say xmatch, oops, xmatch, my tab complete is still running annoyingly slowly, against dice. That would work basically the same. This one I think actually, yeah, I did it based on the bow trick, which is to take the Unicode. So if you know, you know. The Unicode for the dice characters is 6 consecutive numbers starting from 9856. So if you take the Unicode of a dice and subtract off 9855, then you get the number of pips. Or instead of having to remember that random 4-digit number, you can just define a lambda, a very simple one. That's all it is. Lambda of a dice, Unicode of the dice, minus 9855. So I guess the only thing to say here, these are pretty similar to some ones of Brits that we already talked about on the channel. The only thing to say here is just a reminder that, lambdas can be very powerful and offer a real kind of timing boost on things that keep coming up over and over again. Just, a release on your working memory of like not having to remember 9855 or whatever, even without being, super sophisticated or powerful. These are as basic as can be. Anyway, next, I've got some text stuff. So I got one called count occurrence, which again, I'm going to switch to using the advanced formula environment in a minute, but these are pretty simple ones, so let's just take it. So given a string and a substring, we take the length of the string minus the length of the string if we substitute out the substring, and then divide by the length of the substring. So this part here is like a very, very standard trick. Like, you want to know how many A's are in this, you measure the length of it, and then you measure how much shorter it gets if you take out all the A's. At some point, I stuffed up when I was counting the number of something that was 2 characters long and forgot to divide by 2, and lost like a bonus question or something for that, which again is a reminder that if you have a lambda that standardizes your logic and keeps it all in one place and kind of manages the edge cases, then you don't have to worry about forgetting about that, or you don't have to worry about remembering the kind of finer details. That there's nothing super sophisticated about this formula, but it is like, it's not a built-in function, and it feels at times like it really should be because it's so standard. And so this is like a very standard hack to get around it, but it's much less straightforward than just writing a standard function. This is, again, very much the kind of thing in my mind that deserves to have a lambda. Big warning, it is case sensitive because by default the substitute function, well, by default the only way, the substitute function is case sensitive. So if I substitute out that, I've still got my lowercase a's here and here, and there might be another, no, there's only 2. Anyway, so I put a note here, but I haven't actually done it, to say I should probably add an option for that and default to case insensitive, because case insensitive is normally what I want. So I think the way that I would ideally kind of change the signature of this would be, an optional third argument to say be case sensitive, but that if that was not selected, it would lowercase everything before operating. Anyways, that's count occurrence. The other one is letters, which again, a very standard trick. You take mid of a string, sequence of len of the string, and in steps of 1. And that gives you all the letters in the string laid out. This one has, I guess I should say, I'm tempted to rewrite this one in with regex, which would be regex extract from text, and the pattern can just be period, which matches any character, and return all matches. By default, it spills along a row, which I don't love, but you could wrap it in 2col. The reason that this might be preferable is because of emojis. So let's just grab an emoji. Oh, that looks completely different up here than it looks down there, but whatever. Anyway, so we'll grab that, and let's just see. Yeah, so the regex version is getting that right. This, wait, are we pointing at the wrong? Yes, we're pointing at the wrong one to get it. But let's go up here. This is not getting it because I've got a video talking about this in the Excel bootcamp if you want to know more about it. But basically, the idea is some emojis are 2 characters long for weird reasons. So regex understands that this is only 1 character. Mid does not understand that. So that's my temptation to rewrite it in terms of regex. But the flip side of that is I'm very conscious of compatibility as I write these, because ultimately I'm writing these to use them in Vegas to be competitive, and everyone is on the same version of Excel in Vegas, which is 365, but not Insider Channel. And so right now, regex functions are still in beta and only on the Insider Channel. So unless they're in public release, I'm not going to use anything that requires regex in Vegas, because I won't be able to. So that's one potential rewrite. Another thing that I've thought about is it would be helpful to have an optional argument to give the output in reverse. It's not that hard to reverse it, but that's not something that comes up all that infrequently. So those are a couple of things that I would like to think about changing, but in terms of things I have done, you can take the word a certain number of characters at a time, and I don't know why I call this split, because I can't really interpret that. I know what it's meant to mean, but I don't know which way around it is. But so, for example, if I take this in 4s, then you get, interesting, that's not the way around that I would like to have the default. I'm not sure why I wrote it that way. But anyway, it gives you every consecutive 4 characters. So you got ADGK, then you got DGKL, or I guess this was the logic. If that's the default, then this is saying split it into fours. So you get the first four and then the next four and then the next four, because there are various cases where like you want to split into clumps of 2 arrows. From one of Peter's cases, you want to split into turns of 4 dice rolls or whatever. So that's what those two are for. So this is splitting it into fours without overlap, and this is splitting it into fours with overlap. Again, pretty basic stuff. It's none of it is going to be transformational in competition, but every time that you write mid this sequence len that blah 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 blah, it just takes a lot longer than just writing letters. So that's the idea there. Okay, then arrows is next. Arrows come up all the time. And so I've got a few things here. First, there's just, again, an array constant with the 8 arrows. I have them laid out with the sort of 4 cardinal directions, up, down, left, right first, and then the diagonals, because there are cases where you're only interested in the up, down, left, right. Then I've got, again, another array constant, which is just the left, right component of this. So, you're subtracting. I don't know why, again, I named these left, right, and up, down as opposed to like rows and columns, which always confuses me because I need to think of it. If I use it in an offset or an indirect or anything like that, I need to think of it in terms of row and column changes. But anyway, whatever. That's what I did, and I haven't changed it since. But that's probably on the list of future edits. Anyway, so this is just saying you're moving to the left. Okay, so that's -1 for left, right. This is +1 for left, right. Up and down don't involve any left, right movement, and then this one goes left, this one goes right, this one goes left, this one goes right, and then the same thing for up and down. These don't involve any up and down movement. I think of up as reducing the number of rows by 1, so that's a negative, and down is a positive. So that's that, and then I just have one called ars all, which just stacks those 3 things together, because I will very often want to, look an arrow up in here returning from this one or both. And so this is just a quick way to dump everything into the grid. And then I've got this one called ars comb, which actually, at this point, let's go and look at it in. Oops, wrong. That here. How can I get back to here? We are. Ars comb, here it is. So, you're behind my face. That's kind of annoying. Hang on, I'm gonna have to move myself. Okay, hey presto, now I'm up here. So this is, well, let's just explain the logic first. So the logic is that you'll take 1,000 times the left-right offset and 1 times the up-down offset, or there's an option to give different multiples. So, sorry, 1 times the left-right and 1,000 times the up-down. So this is the left-right arrows times the multiple if you give a multiple, otherwise times 1, and plus the up-down arrows times, again, the multiple if you give a multiple, otherwise 1,000. So I'll show you more about this when we come to talking about maps and the row column reference. If you've seen my videos or Bo's videos, this concept of a unique numerical address can be quite helpful in terms of like flattening a grid, finding neighbors, just like collapsing 2 dimensions of movement down into a single thing. But enough said about that for right now. That's what that one does. I also have just for whatever reason, I laid these ones across horizontally and these ones vertically. Don't ask me why. But I have a knight's moves as left, rights, and up, downs, and a knight combination. And then I also have a lambda that just does combined directions. So you can give it any set of left-right directions and a multiple, any set of up-down directions and a multiple, and it'll give you the combination for that. So in theory, if I had some, weird different thing that moves, not like a knight and not like arrows, I could lay out, a table of the left, right, and a table of the up, down, and get this kind of combined direction thing as well. I don't know if I've ever used this one. I don't know if I've ever used either of these ones either, because I don't think chess has come up since I wrote these. But anyway, it wasn't hard to add given what I already had. So that's arrows. Cards, again, just a few handy array constants. One is the list of suits. The other is the list of opposite suits. So in other words, the other suit of the same color. So diamond goes to heart, heart goes to diamond, spade goes to club, club goes to spade. And then the card order, which is just the first character in order and stored as text. And the reason that it is in order and stored as text is so that I can, well, let's just see, I'll do this and to row of suits. So if I have a bunch of kind of card inputs like this, obviously these ones should be tens, but then I can say something like X match left of this against card order. Wow, what are you doing? Card order. Oh, sorry, I know what I'm doing. I forgot to close left. So, you like, I guess the logic for this was I found myself using like either text before suits or, left of this by the len of this -1 to get the card type out, because there was this one single one that was 2 characters long, but 1 doesn't appear anywhere else. So it seemed much more logical to just take out the left character. But then if you just take out the left character and sort them, then they sort weird. So like this is 10 comes before all the rest of the numbers, and Jack, Queen, King, Ace are not in the right order. And again, this partly stemmed from at some point I did this and thought, okay, yeah, I'll just make a couple of manual fixes. So I got to put Ace at the end and whatever else I had to do. I'll put Jack here and Queen here and King and blah, blah, blah. And I missed one. And so all my workings ended up being somewhat broken. So that was kind of annoying. So yeah, again, just a simple array constant. So yeah, it says it here. First character in order as text, so that you can match on left of card to sort. And this one has the ace at the top. I guess maybe I should do one that has it at the bottom as well. I don't know. Anyway, wouldn't be too hard to just grab this, paste, cut there, and give that a new name for this case, TMP name or whatever. So that's the card stuff. Bit of miscellaneous stuff. You've probably seen me use this one a bunch if you watch my videos. I've just got one called most of. It's pretty similar to group by, except that it predates group by. Group by only just came into general release, but if you group a list by as the row fields and the values and use rows to count the number of occurrences, and then if you do 0, 0, and -2, you get basically the same thing. So the idea is it's getting the unique values that are in here, it's getting the count of each of those, and then it's sorting the whole thing in descending order. And I think there's an optional argument also to say, oh yeah, so you can do minus, I thought you could do, okay, well, let's go and look at what this actually does. So we go home, Excel Labs, let's look at most of. So what's going on here? Why is this so small? It really should be able to be bigger than this, but anyway. Okay, so you've got first you to call the range drop blanks, drop errors, and then take unique of that, so you get the unique values. Then you're counting how many of each of those, and then oh right, yeah, okay, I was being stupid. Because the default is -1, because the default is sort descending, so I could change it to 1. If I wanted to know which was the least of. That makes sense. And then there's an optional one to say only, which tells you how many of the most common thing there are, because that's just a question that gets asked a lot in esports. Again, somewhat unnecessary now that there's group by, although it's still definitely faster to just say most of than to do the whole. This also works. Let me just grab all of this and do that. This works with a 2D array, whereas for group by you have to flatten it first. So sorry, let's just do that again. So if you wanted to do this with group by, you'd have to say group by to call stupid autocomplete. To call of all this, comma, to call of all this, comma rows, comma, 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 minus 2. No, wait, one of those commas. That seems to be the right number of commas. I don't know. Anyway, one of these has to be a 0 to explicitly remove totals or something. Anyway, but you can see it's just a lot more characters to type again versus just most of. And again, this one is specifically thinking of this question comes up in bonus questions all the time. So saving 10 seconds if only the first 2 people are going to get a bonus point is a help. Then I've got 2 others which are called NXT for next and prev for previous. So given an array, and let's just get rid of this again. So given this array, it says what's the next value. So in other words, the next one after 3 is this 4, the next one after that 4 is a 1, and then obviously for the last one there is no next value, and by default it just puts in an x. You can have optional arguments to say next by how many. So in other words, here's what comes 2 later. So 2 after the 3 is that 1, 2 after the 4 is that 6. So this one starts off 1, 6, 3, 3, 3, etc. And ends with 2 x's because again for the last 2 there is nothing 2 steps later. And you can also say what value you want to fill with. So it could be q instead of x or something like that, just because maybe these are x's and y's and you don't want x as the fill. But again, my focus is always on make as many arguments optional with sensible defaults for how I'll usually use them as possible. So you can use this with just an array. And prev, same thing. So here I'm saying, offset by 4 and fill with NAs. So the first 4 are NAs, and then the previous from the fifth, the 4 steps back from the 5th one is the first one, which is the 3, and then so on down. One thing that I've noticed coming up a good bit recently that I use this for is it's for thinking about runs. So you can say like this equals prev of this, and you could wrap it with a minus minus, make it a little easier to see. So like here I've got a second 3 in a row. Here I've got a third 3 in a row, and so you can scan this with something like scan 0, all that stuff, lambda AVA times V plus 1, and that will give you the number. So here's 1, 3, 1, 4, 1, 1, 1, 6. Here's a first 3, a second 3, a third 3 in a run. Then here's a first 2, a second 2 in a run. So yeah, I don't know. That's another one that's kind of on my list that at some point I should probably just make a lambda that goes directly to runs and some other things like that. But that's what that is. Okay. Per-com, I'm not going to talk a whole ton about. This is Bo's function, but I just added it into my Lambda workbook because it is great and super useful. So the basic idea is you can list all the combinations of C things from N things. So given 5 things, how can you pick all the different possible combinations of 3 of those? So you can take the first, second, and third, first, second, and fourth, first, second, and fifth. Then there are options for whether you want to allow repetition or not. So this is the version where you can say 1, 2. You can also say 2, 1. So in other words, the order doesn't matter, but you can't pick 1 twice. So this is the default version is that you can. It's permutations rather than combinations. I should have said, I guess, that it's called per-com because of permutations and combinations. So here you can have different orders. Then you can add an optional argument to say no different orders. So in this case, they're all in ascending order. So there's 1, 2, but there's not 2, 1. You have an option to allow repetition, in which case you can have basically you get all. So you get 1 and everything, you get 2 and everything, you get 3 and everything, you get 4 and everything, and you get 5 and everything. And you have an option to allow repetitions, but still be strict on order. So here you get 1 followed by 1, 2, 3, 4, 5, 2 followed by 2, 3, 4, 5, 3 followed by 3, 4, 5, 4 followed by 4, 5, and 5 followed by 5. These are super useful in lots of different things. One word of warning is I don't even remember which version I have in here. Bo has written other versions of this that are more flexible on this count, but the word of warning here is that I think this version only handles single digits. So if you say percom, let's say choosing two things from 10 without repetition, I think it's 1-1 for the most restrictive version. This is going to behave weird. So you won't ever get a 10 in there. That's because that's just not what this was written for. So this one only goes single digit. Again, there are ways. Bo has done a lot of them at different times. There are ways to rewrite this so that it'll handle bigger sets, but I'm not really gonna show you this one particularly, but I'll just flash it up again. I've made a video discussing this one before, based on Michael Jarman's crazy dicey battle case. It was super useful for that. There's a lot of cleverness going on in here to make this a single function for so many different cases. I'm not going to attempt to show you all of it now. Okay, then I've got a few things for maps, because again, maps come up often. So a couple of basic ones. One is just addresses. You give it a range, it gives you the addresses. The function is super simple. Address of row of range, column of range, and 4. 4 is the optional argument to make it not include any dollar signs, so you get a relative reference. That's very handy. Then this row column, I've talked before about this idea of having, rather than having this where you have to split up, okay, what's the kind of letter bit that tells you the column, what's the number bit that tells you the row, then how do you shift from there, blah, blah, blah. If you reduce it down to a single variable, the logic for, going up in steps of 1,000 for rows rather than just whatever, 1, 2, 3, 4, and then start again here at 5, 6, 7, 8, is that if you add 1 to 4, corresponding to going to the right, you don't want to end up here. You want to end up off the grid and know that you're off the grid. So that's why it goes in steps of 1 left to right, but in steps of 1,000 up and down. And again, this one has optional arguments if you want to change the multiple, but I rarely change the multiple. These things in combination, what is all this? Oh yeah. These things in combination can be very powerful if you like flatten. So let's say we flatten the map itself, and then we flatten the addresses of the map, and we flatten the row column of the map. Then you can start to do some more interesting things with this. And one thing that you can do with it is, if I take my arscom, sorry. So these are all the 8 different directions that you can go in one space around it. So then I can say, give me this plus this. So these are all the places you can get to from here. And then you can also figure out which of those are in the map by X matching that against this. So you can see, you can't step to the left from the top left cell, you can't step up from the top left cell, you can't step up into the left from the top left cell, or down into the left or up into the right or whatever. But if you step down, you get to the thing that's in row 2. And so here you can say something like index. So let's say you want to know the neighbors of a thing. You could say index that on X match that, and then you might want to wrap it in an if NA. So you can say the neighbors of this S in the top left corner are a U to the right, an X below, and a J below and to the right. There's lots of other things you can do with this, but it's just to give you a sort of taste. Okay, and this, I was just playing around with something. Okay, so then the last two are some of the funkier ones, but also some of the cooler ones. So this one is called dist from, and the idea is for a given grid and for a given target, how far away are you from that target? So, here you've got jacks here, here, and here, which correspond to the 0 distances here, here, and here, here, and here. So if you measure distance by, this is a step and this is a step, then this is your distance away from the closest jack. So this is 3 away, this is 3 away, this is 2 away from this one, this is 2 away from this one, and so on. But the cool thing is, this function is what function gets applied to the two differences, to the row difference and the column difference, to figure out the distance. So if you're using this kind of taxi cab version where that's a step and that's a step and that's a step and that's a step and the only steps are up, down, left, right, then you can use sum to get that. If you're using what comes up quite commonly in esports where a diagonal is also just one step, then you can just take the min of the two distances, the max of the two distances. And so then you get, okay, all of these squares are reachable in one. This one is reachable in two by going one diagonal step and one step that way. This one diagonal step and one that way. This one diagonal step and one that way, and so on. The other fun one that you can do is you can use sum of squares, to give you, it'll give you the square, but it'll give you the Pythagorean distance, as came up in Harry's census case recently. And you could wrap that in a square root if you want the actual Pythagorean distance, and that would allow you to think about, what's within, X distance of the water, or X distance of the nearest town, or X distance of the nearest hospital. Like this kind of distance from the nearest thing comes up a lot in esports cases. So let me just show you the way this one is written, because this ability to pass functions does definitely help in terms of flexibility. So dist from, here it is. So I don't know why this will only give me this much of the real estate, but anyway, okay. So you give it a map, a target, and a function. So first we get the values, which is just flatten the map. Then you get the row numbers, which is just, basically fill in 1 in the first row, 2 in the second row, 3 in the third row, and then flatten that. The column numbers, which again, fill in 1 in the first column, 2 in the second column, and flatten that. Then, I don't know why I called it M rows and M cols, but anyway, these are the rows and columns of the target, but flattened out across. So you get all the rows and columns down the side, and then along the top you get a row of the row numbers where the value is equal to the target, so in this case where it's equal to jack, and the column numbers where it's equal to jack. And then using broadcast, you get the difference between those two, so the row distance, which is the absolute value of the rows, which is a column, minus the target rows, again, I don't know why I called it M, which is a row, gives you a 2D block of row distances as absolute value, a 2D block of column distances as absolute value. And then this is where the cool stuff happens. So you map the row distance and the column distance and apply this function to each pair of row distance and column distance. So if you sum the row distance and the column distance, you get the taxi cab distance. If you take the max, you get the distance where a diagonal step is 1. If you take the sum of the squares, you get the square of the Pythagorean distance. Or you can put in other functions here. So that gives you a blob, a 2D array, which is, from every position to every target, what is the distance, and then you just do by row on that to take the minimum. So in other words, across all the targets, which is the closest distance. And then just for display purposes, you wrap, so that gives you an array of distances that has a single column with the number of entries in the whole map, and then you just wrap that back into the same shape as the original map for the output, which I think is pretty cool. The other nice thing is, so there's sort of standard functions that you can use for standard distances, but you can also, like I just made a quick thing here, if you remember Nick Boberg's diving case, there was a weird distance function where you could go diagonally, and that cost 5. You could go to the side, and that cost 3. You could go up and down, and that cost 4. So you can also put in a custom function here. So in this case, it says, given a row and a column, we're going to take 5 times the smaller of those, plus if there's more rows than columns, then take 4 times the difference, and if there's more columns than rows, then take 3 times that difference. And that will give you the Nick Boberg distance from the nearest target. So, here you can go up and it costs 4, you can go diagonal and it costs 5. To get to this one, you're going to have to go diagonal and then left, or left and then diagonal, or something like that. So you can also do this with a custom distance function, which I think is pretty cool. And then the last one I'm going to show you is neighbor op. This is actually the first one. There's a one that I wrote before the plane journey, because I thought it was kind of fun. So the idea of neighbor op is, let's start with something more basic. Neighbor op, let's just do, so you give it a grid, you give it a distance, and you give it a function. So let's just take a simple one. On this grid, within a distance of 1, concat. And what it gives you is it finds all the neighbors within a distance of 1 on this grid. And this is just kind of distance in the square centered on that place sense. So from here there are 9 neighbors, from here there are 4 neighbors, from here there are 6 neighbors, and so it respects the boundaries of the grid, and then it applies whatever function you want to that. So here's all the things. There's suxj, there's suwxjl, and so on. But you can apply any function you want. This was, I think, originally inspired by Bear Island. And so, the idea there was, when you had bears that had a certain range, so you needed to know which squares were not safe to go to because they were within range of a bear. So, sort of the equivalent in this case of, oh, that's weird, that's new. Sorry, don't let me get distracted. That like all these squares would be out of bounds because they're within 1 of a bear. And so that's, this is saying, rather than just take the range, we're saying minus minus that equals j. So 1 if it's a jack, 0 bear, whatever, 0 otherwise, within a range of 1, and sum. And that'll tell you how many jacks are within 1 of this. So there's like 2 squares here that are both within range of this one. There's 3 squares here that are both within range of this one. So you get 2's here and 2's here. The only squares that are not next to a jack are these ones over here and over here. And you can also do, you can do it with a range of 2. So that you'd see whatever, this square within a range of 2 can reach all 3 bears. So that one, all 3 jacks, all 3 bears. So that one gets a 3. I guess all of this row can reach them all. So that whole row gets 3's. And then the rest can only reach, either this one or this one. So that is neighbor op. I'm trying to think if there's anything else to tell you about. I mean, again, you can put in a different custom function here, but that's basically the idea. So if you're thinking, whatever, is there an alien within 5 spaces of you, or like the Game of Life came up recently in the South African Excel Championship, and this was kind of perfect for that, because you could say, okay, if you have a grid that says where is their life, then you can very quickly figure out the neighbors of where you are. Now, I will say this this can run a little slowly on a big map. The way this works, let's just show you. Neighbor up, neighbor up, neighbor up, neighbor up, neighbor up here. So it makes an array of the same dimensions as the original map, and then for any given R and C, it applies the function to the grid that it gets by. So define the first row as you subtract the distance from the row you're in, but it has to be at least 1. First column, same idea, you subtract the distance from the column you're in, but it has to be at least 1. So that's how you make it respect the boundaries. And similarly, for the last row and column, you add the distance, but you limit it to the number of rows in the range, or you limit it to the number of columns in the range. And then I use choose calls, so choose rows and choose calls, to pick pick the columns between first row number and last row number, and pick the rows between first row number and last row number, and pick the columns between first column number and last column number, and then apply my custom function, whatever that is. Or it doesn't have to be a custom function, my native or custom function, to that whole thing. That is neighbor op, and that is basically it. I've included my esports macros here as well. I think I've possibly shared these before with the esports bootcamp, but anyway, very simple things. This one just filters, makes a copy of the case sheet, relies on lots of things staying the same, but they usually do, like the fact that the sheet is called case, the fact that the game numbers are in column B, and so on. So it makes a copy of the sheet, deletes all the drawing objects because there's a bunch of stuff sitting on top, unmerges cells, and then filters it so that it's only game numbers excluding examples. This one I've definitely demoed before. It kind of colors a map, so that Actually, these ones are, well, like you could color this with, orange one color and yellow another color. Um, and then this one does the reverse of that, which is color number though. Oh yeah, sorry. So this is going from like a color number. So this fills each cell with the number of its color. And then you can go in the other direction. If you pull out a unique list of those, you can color those so that you get a legend, basically. But anyway, I think I've shared all of those before. And then LAMBDA I've done a specific video on recently, so not going to labor the point on that one, but this is just an example of that for completeness. And that's it. This video has become very long and also not as well planned and organized as I would have liked, but like I said, I really wanted to get these out there before the first round kicked off, so now at least I will do that. That's all I got for today. Thanks for watching. See you next time.